All right, picture this for a second. Imagine you're a detective. You're handed a 2-hour surveillance tape, and your boss asks you to find out exactly when a suspect dropped a very specific piece of evidence. Now, do you just sit there staring blankly at the screen for 2 straight hours, absorbing every single irrelevant frame? Well, of course not. You'd fast forward, you'd skip around, you'd scan for specific visual cues, or maybe listen for a sudden noise. Basically, you'd actively search. Yet for the longest time, artificial intelligence models have approached video like, well, a passive couch potato. They're basically forced to watch every single second of the haystack just to find the needle. And that computational bottleneck, that's exactly what we are unspooling today.
Welcome to today's Explainer, where we're going to dive really deep into a groundbreaking framework called OmniAgent. This is a new system that completely reimagines multimodal large language models. It takes them from being these passive observers and turns them into native, active perceivers. It literally transforms the AI into a true detective, completely rethinking how machines understand long-form video. Here is our roadmap for this explainer. First up, we'll look at the long video bottleneck. Then, enter active perception. Third, the observation thought action loop. After that, solving the credit problem. And finally, doing more with less.
Okay, kicking things off with section 1, the long video bottleneck, or what we like to call the watch-it-all problem. Let's really look at the fundamental flaw in how traditional AI models handle video.
Think about how standard passive AI models work. They use this watch-it-all paradigm, meaning they process every single video frame uniformly. It doesn't matter if you're asking a super simple question or an incredibly complex one. They watch the whole thing. The huge problem here is high dimensionality. As the video gets longer, the computational cost doesn't just grow, it explodes superlinearly. Processing an hour-long video becomes impossibly expensive. But an active model? It operates on demand. Its computational cost doesn't actually scale with the length of the raw video. It scales based on the complexity of the query itself. Which brings us nicely to section 2. Enter active perception, the AI detective. To solve this massive scaling nightmare, researchers built OmniAgent. Now, I really want to take our time here and thoroughly break down this core architecture diagram, because this is absolutely the heart of the entire system. We need to understand every piece of this. If you look over on the far left, you'll see the persistent memory. I want you to think of this as the detective's physical notebook. Moving to the middle, we have the OmniAgent brain itself, which acts as the central processor driving the observation thought action cycle that you see over on the right side. Now, here is where it gets really interesting. When a user asks a question, the agent down at the bottom doesn't just ingest the entire raw video, not at all. Instead, it executes a very specific action, maybe fetching a short audio clip or just a few key visual frames. The environment then fetches this small slice of data, labeled here as the transient percept. But here is the absolute genius part of the diagram. The agent observes those few frames, extracts the relevant details, writes them down as text notes in its memory, and then, if you notice that little recycle symbol, it actively purges the heavy raw video files from its active context. It literally throws the heavy media away once it has the clues. This persistent textual memory that we just looked at, this is the secret sauce. By distilling those heavy, high-dimensional audio and visual cues into compact text, the model successfully decouples its reasoning complexity from the duration of the raw video. This means the model's memory footprint stays incredibly late. It doesn't matter if the video is 3 minutes long or 3 hours long, because it only holds on to the text notes it has gathered. Moving right along to section 3, the observation, thought, action loop, the detective cycle. So how does this AI detective actually decide what clue to look for next? Let's really unpack the steps shown here, zooming in on that cycle from the right side of the architecture diagram. OmniAgent treats perception as a continuous iterative reasoning process. We call this the observation thought action loop, or OTA for short. It's a 3-step cycle, and it's vital to understand how they flow into each other. Step 1 is observation. The model looks at the small clip it requested and summarizes what it just saw or heard directly into its text memory. Step 2 is thought. The AI detective takes a moment to analyze its notebook, looks back at the user's original query, and logically figures out, okay, what evidence am I still missing? Finally, step 3 is action. Based entirely on that thought process, it decides exactly what specific sensory information it needs to go out and retrieve next to fill that missing evidence gap. Then the cycle repeats. So what exactly is in this detective's toolkit to execute those actions? Well, it has a few very specific options. It can use get_frames to jump to a specific timestamp and just grab a few still images, which is perfect for a quick visual scan. It can use Get Audio to pull acoustic context. Think of this like specifically listening for a siren or waiting to hear a certain name spoken. If it really needs to see motion, it can trigger Get Clip, which captures the synced audio-visual dynamics. And finally, when its confidence is high enough that it has actually solved the mystery, it selects the Answer action. This terminates the search completely and delivers the final result to the user. Okay, Section 4, Solving the Credit Problem. Training the detective. Now, actually training an AI to think in this complex, multi-step, cyclical way, it's not easy. You have to figure out how to reward it for making good choices. Now, if you look at this comparison, standard reinforcement learning uses something called vanilla GRPO. It essentially gives a uniform flat reward for the entire string of actions as long as the model eventually gets the final answer right. But that creates a huge problem known as advantage homogenization. It means the AI gets the exact same credit for a totally trivial fast-forward action as it does for the pivotal aha moment where it discovered the murder weapon. That doesn't make sense, right? To fix this, the researchers invented a new method called TARA. TARA is brilliant because it assigns credit turn by turn based on token entropy. It deliberately steers the biggest rewards specifically toward those critical fork-in-the-road moments of discovery. And the data backs this up perfectly. Just look at this stat. The crucial point is how TARA actually identifies those aha moments. It uses entropy, which is a mathematical measure of the model's uncertainty. The data showed that almost 80% of the time, when the AI is at a critical fork in the road, say it's ruling out 3 suspects and deciding to zoom in on a 4th, its entropy naturally spikes because it's actively weighing very complex diverging paths. TARA intelligently uses this spike in uncertainty as a direct signal to amplify the reward for that specific, highly valuable reasoning turn. Finally, Section 5, Doing more with less. Let's look at the actual proof. We've talked a lot about the architecture and the training theory, but does this active perception approach actually work in the real world? I want to spend a moment here to make sure this graph is crystal clear because it perfectly visualizes the system in practice. We're looking at test time scaling on the video MME long benchmark. Let's break down the axes. The solid red line represents the model's accuracy, and the x-axis along the bottom is the maximum number of reasoning turns the model is actually allowed to take. As you can clearly see, as you give OmniAgent a larger budget to think and take more turns, that red accuracy line climbs steadily, reaching up to 59.6%. But you also need to look at those blue bars. Those represent the actual average turns the model consumed to get the answer. Notice how, even when it is allowed a massive budget of up to 52 turns, the blue bars naturally flatten out and saturate around 11.7 turns. It doesn't just blindly use up compute because it can. It stops actively searching the exact moment it has gathered enough evidence to confidently answer the question. It's incredibly efficient. Now, look at this plot for the extreme long video benchmark LV bench. This is a fascinating visual. See all those massive blue bubbles clustered together? Those represent the massive traditional passive models. As you can see by their position on the x-axis, they require hundreds and hundreds of frames just to function, and their accuracy on the y-axis is kind of middling. But look for that red diamond. It's sitting completely alone way up in the top left corner of the chart. That right there is OmniAgent. It's achieving the absolute highest accuracy of the entire group while processing an incredibly, almost shockingly low number of visual frames. It completely breaks the curve. Let me just pause and emphasize this number to put a hard figure on what we just saw in that chart. OmniAgent uses 73% fewer frames than its massive passive competitors. Because it actively searches, it literally just ignores the vast majority of useless repetitive video data. It literally is a David versus Goliath situation, and this comparison highlights it perfectly. OmniAgent is a 7 billion parameter model, a relatively small footprint. Yet it achieves 50.5% accuracy using only about 203 frames, and the whole thing runs smoothly on a single GPU. It outright beats a model that is 10 times its size, the QN 2.5VL72B. That Goliath model scored lower accuracy, required a dense 768 frames, and needed 4 full GPUs just to run. This proves that active perception acts as a massive computation multiplier. And we're seeing this dominance across the board. This wasn't just a one-off lucky victory. OmniAgent established state-of-the-art results for open-source models everywhere. It dominated long video comprehension benchmarks like MLVU at 71.1%. It excelled in complex joint audiovisual tasks like Daily Omni, and perhaps the most mind-blowing stat, it achieved a massive 33.4% absolute gain in temporal grounding on long val. That means it is incredibly precise at pointing out exactly when a specific event occurred in a long timeline. So by treating perception not as a passive sponge but as an active, query-driven investigation, OmniAgent has completely decoupled task complexity from video duration. It literally only looks where it needs to look. Which leaves us with a truly fascinating thought to end on today. If AI can now actively investigate and interrogate our world instead of just passively watching it, what complex mysteries will we ask it to solve next? Thanks so much for joining me on this explainer, and keep exploring.